With this little presentation, I wanted to highlight and try to convince you that possibly hydrothermal vent, deep sea vent system could be cradles for the origin of life. So we're going to review different kind of example. What are hydrothermal vents? How can we study them? How can we reproduce this condition at lab scale with different equipment? And I will give a little bit of example concerning what has been done so far. So I would like to thank Anaïs Cario, who is right here, and also Cindy, right there, and Grégoire, is right there, okay, for preparing also some slides, because as part of this presentation are also from Cindy and Grégoire literature survey that they did during the early stage of their PhD. So, as a starting point, I like this figure to figure out what was there at the beginning. And if you look at this evolution from atoms to ecosystems, at the beginning is physics. So sorry for microbiologists and others, but physics is definitely here, and I think you had courses already about that earlier this week. Starting from the creation of atoms that combine then with chemistry to form molecules. And then the problem is how to switch from molecules to life and to microbiology. Once you have microbiology, little tiny cells can combine to form microorganisms. Microorganisms will also combine and interact with each other to compete for different kind of things, environmental things, resources and so on. They're going to interact together. And so you start having sociology around. Starting from this point, you also have to deal with politics, because politics and religions are actually some thematics that originate from the interaction of microorganisms, basically us. And especially religion are important, because one of the key questions here is, this is the reason why you are here. Religion asks questions to figure out where we're from. And to answer this question, the point is really to find out how you go from chemistry to microbiology, the origin of life. So origin of life, it's a complex journey from tiny small molecules, what I would call inorganic molecules, water, CO2, ammonia, and so on, that could combine through different type of abiotic chemical reaction, or biotic as well, but in our case we're going to consider abiotic, to form more complex molecules such as amino acid, carbohydrate, and so on, which are the starting point through polymerization to polypeptide proteins, lipids, phospholipids, nucleobased, that can represent basically what we can call prebiotic chemistry. All these elements, you have seen that I think this morning also, are key, the three components, to form, to be encapsulated, to form protocells with self-assembly of lipid phospholipids, for instance, creating chemical gradients through membranes, creating, that is very important, non-equilibrium condition. As soon as you are thermodynamically stable at equilibrium, you have no life. So basically life needs non-equilibrium. And it controls also, this membrane controls the exchanges between the inside of the cells and the external environment. And once this is done, you need to start doing metabolism so that the organism can collect energy, harvest energy, can replicate, and can adapt to its external condition and external environment. So this picture is quite important here, because it's the different, it's a simplified chemical pathway, I would say, but it's some kind of a guideline from these tiny molecules here that could combine in different way to create lipids and phospholipids for compartmentalization, RNA for replication, and proteins for the metabolism. So there are 6 essential ingredients that make up organism, from what we know so far: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, sorry. And so this leads to the possible earliest life, so the Luca guy, that then is divided with the tree of life and you're going to have another courses after this one on more detail about this tree of life. So compartmentalization is quite interesting because we represent this as membrane most of the time, but basically it's more some kind of micro world that can be compared to microreactors. And from my own experience as a scientist, I was initially a chemical engineer, so nothing to do with prebiotic chemistry and so on. And in chemical engineering, a microreactor is basically a micro environment, a micro vessel that is designed to contain a biochemical reaction. And the aim is to maximize the reaction performance towards the highest efficiency. So if you take into account this definition, cells, so that's just what I mentioned before with membrane, blood vessel can be considered as microreactor or micro compartmentalized environment. But zeolite and porous media can be considered also as tiny confined microreactor. In that case, those have organic membrane, but this one is really just a confined environment with small porous structure, small pores, that can furnish a control of the local gradient, higher concentration of molecules in a certain place, meaning that if you consider chemical reaction in very dilute concentration, like a chemical reaction that can occur in the atmosphere, you have few chances to have molecules meeting with each other because they need to get in contact to react. Having this type of higher concentration in those tiny spaces here increase the chemical reactivity. And beside in those environments, especially here, you have high surface to volume ratio, meaning that you can have catalysis through and adsorption on surface, and so chemical reaction through stabilization of reaction intermediate on the surfaces. So the question is how and where did life originate on Earth? So there's not a single answer, I would say. But the thing is, how can we make abiotically this type of molecules that need then to arrange to make the protocells? Could this be done in atmosphere, in ocean? So it's important before we go further to get more insight in early Earth condition to figure out whether this reaction could occur. So that's why in part one I just wanted to make a short introduction on what were the conditions at the end of the adient. This is a timeline here in giga years. So starting from the formation of Earth, basically it's a kind of magma structure on the surface with an atmosphere which is saturated with vaporized silicate, water and CO2, very high temperature, and pressure very high as well, between 3 and 500 bar. All these numbers that I'm giving, it's hypothetic kind of, because we have some clues, but nothing is so that's why the range can be very large at some time depending on the findings. After some time, so it's pretty nearby, the Earth starts cooling down and you have a silicate solidification and the formation of a protocrust around Earth, meaning the temperature was a little bit lower, but still you have a very strong atmosphere of water and CO2 with very high pressure, up to 300 bar. Then keep cooling down, water can precipitate out, typically in this range of temperature, so you're going to tell me that it's above 100 Celsius degrees, so it's not possible that water precipitate. Yes, because the pressure is very high, so you're still above the liquid curve equilibrium. And leaving behind only CO2. So then oceans start forming in that case. The remaining CO2 later on solubilize in the ocean and mineralize through carbonates, for instance. And you start having the plate tectonics that start creating movement between different plates, meaning that silicate can pump CO2 inside the mantle through a subduction zone, basically. At this time, the temperature of the ocean was supposed to be around 70 Celsius degree, and the pressure of CO2 decreased below 10 bar. So this range is basically where we think now, from different evidences, that life originates. And as you can see, the condition of pressure, temperature, and so on have lots of variability. So it's still difficult to figure out, and that's what I need you to keep in mind, to figure out what condition we need to consider if we want to run some experiment to do this chemistry. Because the chemistry is definitely not going to be the same if you consider an ocean at 70 Celsius degree or 300 Celsius degree, or if you have pressure of CO2 of 10 bar or 200 bar. Chemical reactivity would change completely. The hypothesis for an hydrothermalism source of life, potentially, is also due to the fact that the plates were much smaller at the beginning, when the plate tectonic starts. Earth was made of lots of little tectonic plates, and hydrothermalism was effective in between all those plates, so typically at the ridge of the plate, like we have right now. But since the number of plates was very high, the number of hydrothermal potential sites was much higher than what we have right now. So there are different places where life could have started and prebiotic chemistry could have started. So either in deep sea vent or pool, I would say, or on the ground, so the early continent kind of that were above the level of seawater, specifically in tidal pool or little tiny ponds, where you could have also impact of meteorite creating high thermal energy locally that could activate a chemical reaction. I'm going to go very fast through this because I know you had discussed this part before this morning, but the hypothesis of the famous Miller experiment, so it's the hypothesis of atmosphere prebiotic chemistry. Definitely, that's my conclusion. That does work. We had reactive environment, electrical discharge, photoactivation, and basically you can clearly synthesize hydrogen cyanide to form nucleotide potentially towards RNA. You can form formaldehyde to form sugar and possibly amino acids towards peptide and protein. The question is, are we sure of, based on my previous slide before, are we sure of the condition we are considering? So that's one point. Definitely, this is true, and it could work. The question is, at what period are we considering that? Because as soon as the ocean start be creating with the precipitation of water, all the conditions evolve very fast due to CO2 dissolution, decrease of temperature, and so on. So the second one is this warm little pond hypothesis here, so on the ground, with temperatures that were possibly around 100 Celsius degree or maybe a little bit less. Where you have the interest in this approach is that you have reducing environment also, thermal energy, so either from the ground itself or from meteoritic impact, photoactivation during the daylight, and the interesting thing is that this area were possibly submitted to imbibition, dehydration, meaning that during imbibition you have solubilization in water and activation of chemical reaction. And during dehydration, well, so basically everything was dry, you had absorption on different minerals of the molecules that could stabilize reactive intermediates that could react together later on. So it's really the absorption on mineral surface that could catalyze the chemical reaction, plus the addition of a photon that could also do the photoactivation of this type of reaction. And so what I'm going to talk a little bit more today is the last option, one of the last options, I would say, the hydrothermal vent hypothesis. So, like I told you, in the late Hadean, early Archean, the plates were much smaller. So there are many possible sites for deep sea hydrothermal vent, also reductive environment, high and continuous thermal energy from the mantle and the magma and Earth, basically the center of Earth. And interestingly, those things are also the place for a thermal cycle, meaning that the condition can vary, I would say not pretty fast, but quite fast, from high to low temperature, meaning that you can activate molecules without degrading them so fast and having them reacting together. The other interesting thing here is that those structures that I will detail just after are porous media. And we get back to my point before, confined environment, high surface to volume ratio, so potentially lots of surface for molecules and intermediates to fix on mineral surface, higher concentration, and also chemical gradients from one pore to another, for instance, that could be some kind of micro confinement that is needed basically to prevent aggression of the external world inside this pore. So this is my second part about hydrothermal vents. So what are they? Actually, they were discovered for the first time during a mission, a sea mission in the Galapagos in 1977. This mission, the point of this mission, so it's right here, Galapagos, was just to map the seafloor basically in this area, because some variation of height have been seen by sonar. So basically, they use robots basically that you take down to the seafloor. And the robots was just passing by different area, and at some point during the night, one engineer that was working on the project just figured out that the temperature sensor that was on the roof goes pretty fast from 2, 3, 4, 5 Celsius degree up to several hundreds of Celsius degree, and few seconds after back to 2, 3, 4, 5 Celsius degree. It was like, what the hell? We have a hotspot here. What is it due to? They had discovered this hydrothermal vent where actually you have very hot fluid coming out from some seawater that is heated by magma that is flowing through chimneys that are created with salt precipitation. I will detail this just after. And since then, actually, so 45 years ago, people have figured out that actually they are spread everywhere over the world, and mostly during in the spreading or converging the ridge between plates, tectonic plates, at plates boundary. So you have all these different sites, so they can be of different kinds, but typically you have this type of thing almost everywhere. But again, remember my point before. This is what is known so far. If you consider that plate could have been much smaller, you have much more hydrothermal deep sea vent that could have been present in the early age. So first discovery here, and for some of you maybe that were here last year, Anaïs made a presentation, and they went with Isabelle Daniel also for a cruise to sample this the deepest deep sea vent known so far in the Mid-Caribbean. So that's also an interesting point, because those structures are typically at depths between 1,500 meter to 5,000 meter. So they look like this. This is a movie of what you see when you go down there. These chimneys that are formed from the precipitation of iron and manganese and magnesium-rich fluid that are coming out here, that precipitate with sulfur to form generally a sulfide structure here. When they enter in contact, the hot fluid enter in contact with the cold seawater to form this giant chimney that can be up to 40 or 50 meter in height. So imagine the first discovery, the robot is right here, and wow, you see this structure that is completely not expected. So I think they were pretty much surprised. Again, if you look closer, basically, in the case of deep sea vent that we can find right now at this period on Earth, it's full of life. It's really an oasis of life, with lots of micro and microorganisms, lots of porosity also inside the rocks, because no light, but the microorganisms work with our chemotroph, basically they work with chemothermal energy, which could be used also for abiotic chemistry. How does it works for this? So like I said, basically the fluid that is so seawater that is basically sucked from the seafloor have a cycle here, is heated through the magma in the mantle that is loaded with high concentration of hydrogen through serpentinization and other geochemical processes, methane, CO2 that dissolve in the seawater, loaded also with the dissolution of minerals, because in this area typically the temperature can go up to 1000 or even more Celsius degree. Water is really under high pressure. And then it's flow back to the seafloor, precipitation, like I said. So the fluid can be sub or supercritical, between 3, 4, 500 Celsius degrees sometimes. And this create when this hydrothermal fluid meets the oxyc sea water to the precipitation of this chimney, generally made, like I said, of pyrite, chalcopyrite, or other kind of things. So it's interesting, like I said, because you have thermal gradient. So from cold here typically to very hot here, with a strong gradient throughout the chimney. Right now, the ocean are oxidized, of course, because we have oxygen. It was not true in the early age. But you have oxygen gradient, but you have also a different type of chemical gradient from inside to outside of the chimney. And so, like I said, pressure can be very high. So the question is how to characterize this chimney. So I told you that typically we took a robot, so that's what people do. This is some picture extracted from the mission of Anaïs and Isabelle Daniel. The US robot Jason that is taken out of the chip down to the seafloor, and then they sample basically the chimney with a robot arm, and you use high pressure equipment that are gas tight, isobaric gas tight, to make sure that you maintain the sample under pressure from the sampling site up to the surface, even if the pressure decreases a lot. So once you have those samples, you can collect rocks, you can collect fluids, and you can basically define different type of smokers, either what we call black smokers, mostly made of sulfur and anhydrite. Anhydrite mostly at the for black smokers that are pretty young, and then sulfide, iron sulfide or copper sulfide and so on. And they're called black smoker because the plume basically that come out of the chimney is very dark. There are other type of smoker which are called white. In that case, the composition is really different. They are mostly made of silicate and barite, with calcium carbonate as well, and also a brucite, so magnesium hydroxide. And the plume are mostly white in color, so that's why it's called white smokers. When you get down there, you can measure velocity, you can measure temperature, and you can characterize those environments. So in black smokers, the velocity of the fluid depends on the pressure that is generated by the temperature of the fluid below the black smoker. So it can go typically from centimeter per second to meter per second, so very high flow rate sometimes. The temperature can be in between 3 and 400 Celsius degree, quite acidic. Anoxic fluid, so rich in silicone, carbon dioxide, H2S, methane, and so on. And lots of transition metal salt, iron 2+, magnesium, zinc, and so on. Whereas white smoker have much lower temperature, typically below 100 Celsius degree. Mostly alkaline compared to what you have in white smokers. And the mineralizing fluid are rich in calcium and sulfate rich, so such as anhydrite, so it's calcium sulfite. And lots of carbonate deposit also, but really poor in H2S. So that means why the chimney are not made out of the same materials. So just to give you a brief overview, I'm not going to detail everything, but once you have the sample, you can do atomic percentage analysis and different type of analysis to figure out ICP and so on, to figure out what are the fluid composition that are exiting the chimney. So like I told you, this is for black smoker here, there's two, and lost city is white smokers. So of course you have sodium chloride, but lots of iron in the case of black smokers, and really small amount in the case of white smokers. So those types are, those two types of hydrothermal vents are different just because it depends on the geomorphological context of their formations. So depending on where they form on Earth, in which circumstances, depending on the rocks that you have, ultramafic rocks or mafic rocks, you're gonna have to. I mean, you're potentially gonna switch from black to white smokers. What is interesting to know is that right now, black smokers are much more present than white smokers so far that we know at this period. But it's clearly envisioned by different type of studies that it was quite the opposite in the early age, mostly made out of white smokers were much more in numbers than black smokers. So possibly, and that's going to make a link to my 3 next slides, a model for black smokers could be an ocean here at between 2 and 6 Celsius degree with oxygen, of course, and nitrate as well, with a pressure of 230 bar. This is the average depth for black smokers. Temperature of the fluid 360 C, pH around 3. Salinity, of course, you have this, but you have also, sodium chloride, but you have also iron chloride in the fluid, and different concentration of gas in the out fluid exiting the chimney. For white smokers, a bit different. So ocean has still the same temperature, of course, because we are below the thermocline, so 2-6 Celsius degree. pH is higher in that case, same concentration of oxygen, but generally white smokers are at depths a little bit less. So basically the pressure is around 80-100 bar. Temperature of the fluid is much smaller, like I said, 30 to 100 Celsius degree. So I give you this information basically to figure out what could be the typical condition we have to use later on to investigate this at lab scale, depending on what we are considering. And so different fluid, different gas also that are dissolved in the vent fluid. So based on different type of hypotheses, like I said, we could consider a definition like this for the hydrothermal late Hadean, early Archean smokers. So like I told you before, it's difficult to figure out what was the actual temperature depending on where we are considering to before or just after the ocean formation, or a little bit later on, because the temperature variation was high. So going from 100 C down to 35 Celsius degree. Salinity was a little bit higher, but in that case, if you want to run an experiment in this condition, of course you get rid of oxygen because there were no oxygen at this time. Oppositely, the water was much richer in CO2 due to the residual pressure of CO2 in the atmosphere. Pressure was probably a little bit lower than black smokers, simply because the continents were not completely formed. It was an early crust. So possibly keeping in mind that the volume of water is more or less the same since this age, the average depth was smaller, shallower than what it is now at some point. No continent, so it's not an ocean world, but possibly the number of emerged surfaces was smaller. So the depth was possibly smaller for this vent. Temperature a little bit lower. There were different studies based on rocks analysis that hypothesized that the formation of these rocks couldn't happen at 300 Celsius degree, for instance, neither at 100 or less Celsius degree. So the temperature of the fluid could have been somewhere in between. Salinity a little bit equivalent to what we have now. An alkalinity between 35 and 40, and a high concentration of CO2 dissolved in the fluid. In terms of minerals, I would say, lots of studies, like different type of papers that you can find here. I've pointed out that what we have right now is mostly magnetite, greigite, pyrite, chalcopyrite, or sphaerite. So those type of system could have been quite the same at this period, with the presence that is validated of olivine, pyrrhotite, and different type of other minerals like maquinawite, sorry. Again, the possibility of rocks that could have been present is huge. So it's difficult, again, everything is difficult, of course, but in this type of science, it's difficult to check, and you cannot investigate thousands of scenarios. It's not possible. I mean, possibly with AI that will be made later on. I will get back to this point later, but we need to identify few conditions and make some assumption to be able to run your experiment and figure out what you get at the end. So hydrothermal vents are also interesting to investigate life that could have arisen elsewhere, because it's now proved that you have ocean world in the solar system, Ganymede, Encelade, Europa, Titan, and so on, with different amount of water. And interestingly, for Encelade and Europe, for instance, thanks to the tidal wave heating of the moon, due to the high attraction of giant gas planet, plus the ratio of orbital periods. So basically, Io is turning one. If Io is turning once around Jupiter, Europa is turning twice, and Ganymede is turning 4 times. And all this provides some tidal wave heating that can provide internal energy to this moon. And we are pretty sure now that you have an ocean world below ice crust, even from the surface, because this looks like ice that is broken at some point. And it was seen also that you have emission of gas from the possible ocean below the ice crust. So what is thought so far is that you could have hydrothermalism, deep sea hydrothermalism, in this world as well. And if we succeed in making a prebiotic chemistry on Earth with hydrothermal vent system, why not elsewhere? But prebiotic chemistry doesn't mean life either. So it's not because we were discussing that during the lunch. It's not because you find methane somewhere that it's a trace of life. A little bit of thermodynamics. So I'm going to talk about water, which is quite an amazing fluid and solvent for life emergence. In particular, when you can take it to conditions that are not conventional, like water that you drink in the conventional room temperature and pressure condition. So that's why I plot this phase diagram, pressure, temperature, for water. So this is a triple point. At low temperature, you have the solid phase, so ice. In between, you have the liquid, gas here, and this is the liquid-gas equilibrium curve. This point is called the critical point. It's basically a point above which condition, so pressure and temperature, you don't have any separation between gas and liquid. It's an homogeneous phase with property, as you can see here, intermediate between those of liquid and those of gas. Density is gas-like, so it can be used as a solvent to run chemistry. Viscosity is more like gas, meaning it's a fluid that can diffuse very fast, even in tiny space, such as porous media. And I will get back to this point after, because the condition of this point here for water is 373 Celsius degree and 221 bar, which are typically the upper condition of hydrothermal fluid that exit black smokers. And those conditions are very interesting because the point of water is high, so like I said, 374 Celsius degree, 221. But all fluid, all molecules have a critical point. For CO2, it's more easy to attain, even experimentally speaking. But you have the same other critical point for ammonia with its relative density. So a supercritical fluid is what? It's basically, if you look, this is just a scheme, a modeling, from interaction between those black dots that are water molecules. During if you take a single snapshot at water at the molecular scale, actually you have liquid-like zone and gas-like zone. And all this evolve very fast, or in the order of few nanoseconds, meaning that the solute can be stabilized by liquid-like area of the water, and the diffusion can be very fast from one point to another through gas-like viscosity. The density of water evolves very fast if you go from 0 to 400 Celsius degree. This is the density, so at 1 bar, density 1, of course, at 0 Celsius or 25 Celsius degree. And then is the first order transition, vaporization from liquid to gas. If you increase the pressure, you go a little bit above in temperature on the gas-liquid equilibrium curve. So you can see the density that is getting down here, and then you switch to the gas phase. And you keep going, 210, and at some point, when you are above the critical pressure, at TC, you have a continuous phase transition in terms of, not phase transition, sorry, density transition from liquid-like to gas-like. But it's a second order transition. It's not a switch from, you don't have any phase transition, because supercritical fluid is not a state of matter, okay? It's something in between gas and liquid. My point here is that supercritical water have a very low density compared to what we have here. Typically you lose basically at 400 Celsius degree, you lose maybe 90% of the density, the initial density. Viscosity is same. Water is not that much viscous, but it's like 1 micropascal per second, and it can go down to a very tiny viscosity when you go to a supercritical water condition. So again, diffusivity is improved. It's a fluid that can really easily penetrate tiny space such as porous media. You don't have that much of pressure drop compared to something that is really viscous. More interestingly, surface tension. Surface tension is 73 millinewton per meter for water at room temperature. And it goes down to 0 because when the fluid is supercritical, you don't have any surface tension. The way I can explain that is that you have the disappearance of the interface between gas and the liquid and water. No surface tension, meaning it's a fluid that can basically wet whatever minerals, whatever materials that you want, bringing whatever is dissolved inside really close to the surface without any non-wetting properties or so on. So it facilitates also the interaction between a dissolved molecule and a mineral or inorganic surface. This example that you can see here, it's also used in other type of processes, because since you have no surface tension in a supercritical condition, you can basically start in the liquid phase, switch to the supercritical domain and get back to gas without any phase transition. Phase transition is complicated because when you have a meniscus in between two particles, you have a surface tension here, okay? And when you evaporate the water, the surface tension will contract the minerals, all the materials together, that can create assemblies. And it's the case in case of when you want to make a gel, for instance, in water. If you vaporize the water here, you will create a zero gel. The structure will collapse. If you go through the supercritical domain, instead of just going like from liquid from gas with evaporation, you don't have any phase transition and you can keep with your gel. So I'm giving this example to tell you that if we have a different kind of long structure that could be proteins, for instance, all these kind of things, they can be stabilized in a certain configuration without any collapsing or changing in the configuration. So the electric constant as well, so like I told you, liquid water is 75, supercritical water is almost 0, and it's quite like hexane. So basically supercritical water is non-polar. Water is polar, supercritical water is non-polar. It can dissolve all organic materials, all organic molecules, like you can do with hexane or ethanol, polar molecules, but it cannot dissolve salt anymore, meaning at supercritical condition, salt will precipitate out, okay? So just to give you an idea, in the vent, inside you have something non-polar that could dissolve organic materials, organic molecules. Outside you have liquid water that can dissolve salt, but not really dissolve organic molecules. So it's another gradient that can be created in such environment just due to the temperature and the property of water. So it's the same solvent, but due to the temperature difference, it's not the same solvent system. And interestingly also, what I wanted to show you is the ionic product of water in terms of chemical reactivity. It goes from the famous 10 to, sorry, it's here the ionic product, but it's this curve. It goes from the famous 10 to the minus 14 at room temperature, Ke, Kw, up to 10 to the minus 11, so 3 orders of magnitude higher, meaning the dissociation, the ionic product is basically the coefficient of the dissociation of water in H plus and OH minus. 10 to the minus 11, 3 orders higher than here at room temperature, means that the water is really dissociated. So it facilitates acido-basic reaction. And the maximum is more or less around 300 Celsius degree. Again, we are close to the condition where the vents are. And when you go a little bit higher, you have a sudden drop after the critical temperature, so 374 Celsius degree, down to 10 to the minus, depending on pressure, 10 to the minus 20 or 24. Meaning in this area, water is really non-dissociated, meaning that we will have mostly radical chemistry in this condition. Nothing will be helped by the dissociation, or you don't have any. You're not going to have any acido-basic type of reaction in that case. The switch is fast, but how do we investigate those conditions at lab scale? So. You've seen the condition of the vent, you've seen the condition of the chemistry when you take into account the property of water, subcritical and supercritical. So it's quite tough to access this condition conventionally. You're not going to use a simple beaker, put your solvent and just run your chemistry. So generally people use stainless steel batch reactor to vary the chemistry, the pressure condition, the temperature. You can dissolve gas inside. Put different organic volatile compound inside. So different example of reactor that can be found in the literature. So this is pretty well known for years or decades, I would say even. The main problem so far is that generally it's time consuming to load everything, to start the experiment, to heat up because you have a huge inertia due to the large volume of the reactor. I mean large volume, it can be smaller, but you have an inertia due to the heating of the reactor. There's the limited control of the operating condition. You have effect of gravity, so you can steer, of course, but you can have a thermal gradient from the bottom to the external. You can have concentration gradient. That could be interesting for what we want to do, but that you cannot really control. So that's the main problem. Plus, when you want to analyze, you have to open your reactor. So it's one shot, it's like you cook something, you know, and then you take out and, oh crap, I failed. So you cannot adjust or change the parameter because you don't know exactly what's happening inside. Besides having information on the temperature, because you can put temperature sensor and pressure sensor. Other equipment that could be used at lab scale, depending on the pressure capacity and their volume, are fluid inclusion. So those are interesting tools because they can be either artificially made. It's little fluid volumes that are trapped in quartz or in different kind of rocks, and that you can monitor under a microscope or with Raman or FTIR spectroscopy and vary the temperature condition, but the volume is fixed. Generally, it's not really well controlled. It's really tiny, but not very well controlled. But the interesting thing is that you can have also natural ones. So if you get the natural sample, you can use this to study that, what happened to the minerals, and get some feedbacks on potential history of the gas composition inside over time due to the chemical reactivity. Diamond enriched cell for really high pressure. So in our case, we are not necessarily considering this type of tools because hydrothermal vent, I mean, what I'm interested in, They are not at more than like we discussed 500 bar. So it's quite could be quite useless, but it's interesting also. Nevertheless, for geochemical analysis, when you go to very deep, like in the mantle or something, to go up to several tenths of gigapascal. Sapphire and glass capillary. So volume can be a little bit higher, so up to liter typically. These are interesting tools because they are easy to implement. They are transparent, so you can put some characterization inside to figure out what's happening during your chemical reaction. And so the autoclaves that I mentioned just before. So if we go through few examples, so a recent one from the team of Isabelle Daniel, by the way, by Muriel Andreani. So there was a fluid inclusion that was collected in Lost City, so it's a white smoker. They recover the rocks, and they figure out that in an olivine crystal that you can see here, they had some fluid inclusion. The interest of this is that you know where it's from, and you can make different type of characterization inside through Raman spectroscopy, FTIR spectroscopy, and map basically the different minerals that you have inside or fluid that you have inside your fluid inclusion to give insight in the prebiotic mechanism. And so that here typically in their paper they mention that initially starting from the end, that's what is characterized, potentially we had a specific chemistry that was involved in this condition with fluid olivine interaction coming from this potential initial composition. And a measure result here, just from a natural sample, is that the water mineral interaction would dry out the water from the sample and pushing the reaction towards pushing the chemical reaction of condensation to combine different small molecules. Again, we start from the end and then we make some assumption. So it can be interesting also to start from the beginning and try to see what we have. But the two options are interesting. Batch reactor, they are commercially used. Here's an example of study just to evaluate different type of chemistry. So we can put in not beaker but in high pressure batch reactor CO2 hydrogen, different type of minerals at the bottom, and get the composition of the gas phase, the evolution of the solid phase at the bottom of the reactor. But it's difficult to catch and make some potential reaction scheme. So here of CO2 with hydrogenation to form formaldehyde and other kind of chemicals later on, depending on the minerals that is involved in the chemistry. But it's difficult to catch reactive intermediate, again, because you cannot put in situ characterization inside. Other example here that were reported, so I'm going to go very fast for this, but batch reactors are interesting because they can account for geochemistry, because you can put minerals inside, recover them after to evaluate the different scenarios, and they account for thermodynamics. But they are batch, so you put it's still during a few hours, few days. You don't account for the fluid flow and so the hydrodynamics. And like I told you, the fluid velocity in vent, for instance, can be pretty high. So it will promote also a mixing of different species. So these are interesting, but not necessarily completely not taking into account all the realistic parameters. So that's why people start doing flow chemistry. So a flow reactor is simple. It's a pump. You pump a liquid, so it could be a fluid that is loaded with different kind of things. So sorry for this mistake. Sulfate and so on. And it flows through a heater, a tubular reactor that is heated. Then you cool it down, you recover your sample, you analyze. Really easy. For instance, this was evaluated for the synthesis of amino acid. It was shown that it was most efficient around Celsius degree in that case. You can do similar things here by mixing different type of fluid. So it's another experiment. It's not a cold tubular reactor in that case. It's just a linear one, and they use aqueous solution of potassium cyanide, to form and formaldehyde, etc., to form different type of molecules, in particular amino acid. Again, corroborating the results of the above system. Around 100 Celsius degree was the maximum range. Temperature range 50 to 400 Celsius degree, and pressure up to 25 MPa. You can see that the reaction time are pretty fast. It's not like millions of years. The reaction can be really fast in this system, mostly because the temperature can reach really, 100 or even above in terms of Celsius degree. It's interesting to have transparent reactor when you work in continuous flow, and I really like this example because they actually were able to grow a chimney inside the transparent reactor here that you have here. So they flow two fluids, they flow one fluid in another. So an hydrothermal fluid at 70 Celsius degree. So this could be more realistic for a white smoker, not really for a late ADN smoker. And the ocean is, the temperature was considered was pretty low here. And basically they were able to grow iron sulfate microcrystal structures that combine together to form this really tiny chimney. So interestingly, with this kind of thing, you can have image monitoring, define speed growth for this type of structure, and evaluate the chemistry. When it's transparent, you can put a probe to do spectroscopy or other kind of thing inside. The problem here is that they were not really in condition representative from the chemistry we want to use. Then you can do co-chemistry as well, with two fluids mixing together, one which is representative from the deep ocean, the other one from the fluid inside the chimney. Mixing together, so here stimulant was salted water at pH 12, and the seawater was, like I mentioned in the previous slide, a little bit more acidic. And the point was to collect the minerals, to figure out the minerals interaction due to this co-injection of fluid. Another one with different other type of minerals, so I'm not going to detail, but the conditions typically are 100 bar of hydrogen, and you try to figure out with this type of a little bit more complex setup how the flow through of different type of fluid can alter the minerals by recovering the minerals at the end and do external characterization. To me, I'm directly interested in that, so to me it's the future for this field of research is microreactor. So I don't know if you guys know about microfluidics, but I will give you a little bit more detail after. Microreactors are generally transparent. You can put them under a microscope, so you can implement lots of characterization techniques. And here, basically, what people did is to mix in a microchannel here one flow of ocean kind of fluid, and the other one, which is representative of the vent fluid. And they were able to monitor the reaction of those inside this tiny channel in the middle. And interestingly, you precipitate a little line of iron sulfate due to the interdiffusion of the two flows together. So same thing can be done with temperature gradient to figure out where and when the precipitation will occur, if you have gas or not, because you have a direct optical access inside the media. It's confined environment, so that's pretty convenient for us to get closer to a porous kind of structure, and you can see through, so you have an optical access to implement characterization techniques. So that's why I wanted to make a short highlight on a project that we recently got with different partners, one US partner and 3 Bordeaux partners, and Anaïs, myself, Cindy and Grégoire are part of this project. The point is actually to study geochemical reaction of deep sea vent. That's probably why I'm here as well, to generate organic molecules. And the main interest we wanted to highlight with this project is develop new approach, combining microfluidic approach and millifluidic approach to study prebiotic chemistry. but also to study hydrothermal vent mineral catalysis to run this chemistry, and doing numerical modeling, coupling experimental data with numerical modeling as well, taking into account thermodynamics, hydrodynamics, and geochemistry. So the point was first to define the early Archean or late Hadean environment, select some prebiotic chemistries. So like I told you, the problem is how do you choose? So we need to fix some kind of system because you cannot investigate everything. And then understand the hydrothermal vent characteristics based on models that we have from the hydrothermal vent that are from today. And extend this to potential hydrothermal vent from the late Hadean, and establish the contribution of hydrothermal vent to this. So microreactor, you've seen this slide before. I showed you that those are membrane compartmentalized, those are confined environment. So let's do this type of things, but in real, with microfluidics. Microfluidics is the flow of tiny quantity of liquid in microchannel. You can make them the way you want because you can design them the way you want, and you can also create porous media inside a microreactor and place this under the microscope to monitor in real time and in real condition your chemical reaction. There's different microreactor technology depending on the pressure and temperature condition that you want to use. First one is conventional PDMS. Maybe you've heard about that. That was the first material to be used to design microfluidic because it's really cheap and easy to fabricate. But then people have done that with ceramics, metal, glass, silicone pyrex. And they have different range of pressure and temperature condition that can be covered. We are interested in this condition. Bless you. That was huge. Metal here, of course, you can go higher in pressure temperature condition, but you lose the optical access. So recently we have developed sapphire microfluidic reactor that really covered all this range of pressure and temperature condition. The interest is that you can go up to 700 bar, 700 Celsius degree, all range of pH, completely neutral chemically speaking. So you're not going to have deterioration of the sapphire unless you use, and that's the way we make them, a mixture of sulfuric acid and phosphoric acid at 300 Celsius degree. So mostly, even for hydrothermal vent condition, we're good. So they're not going to be, they're going to be completely neutral to the environment we want to study. Oppositely to the other technology that we have in the lab, silicone pyrex, where the pyrex can dissolve in subcritical water. You have a certain solubility of silica in subcritical water, meaning that you will dissolve your reactor over time if you use subcritical water. So like I was telling you, the design can be made the way you want. So you can simulate a fluid flow from one side, from the other. You can make porous media. You can make mixing zone, temperature gradient from here to here. And you can implement online and in-situ characterization. So that's interesting because your chip, your microreactor can be placed under, like I was mentioning, on the microscope. So you can combine confocal microscopy, Raman spectroscopy, IR, confocal imaging. Micro-PIV is to monitor the fluid flow. You put some particle tracer inside and you monitor the movement to get back to the fluid velocity. And this is a microreactor with a compression part here that interfaces the microreactor with the external world, pump, pressure sensor, and so on, under the microscope. So you can have lots of information of what's going on inside in real time compared to batch reactor. An example, FTIR mapping, chemical or biochemical mapping inside a reactor. So you have plots here that represent a porous media, and you have a bubble of CO2 in brine. Brine is here, CO2 is here. So it's obvious for us because we know who is weighting what. So we know that CO2 is here. But if you don't know and you don't know the composition, you can do FTIR and get access to mapping. So here's CO2, and here is water, for instance. So you can detect methane, you can detect different kind of things. So that's also something that is interesting for this type of thing. You can manipulate fluid at different pressure and temperature condition. Here's the hydrogen, CO2 and water segmented flow, 200 micron here, hexane in water, and well, I'm going to skip this one because I'm going to run out of time. And so, getting back to hydrothermal vent, can we make microreactor that could be ultra-fast screening tools to screen chemical reaction in probiotic chemistry at hydrothermal vent condition? So remember I told you that the fluid is going out here, but then it's sucked also from the seafloor here, back here. So basically you have long-term thermal cycle, what is called the hydrothermal pump, that arise and that could go from high temperature to low temperature, back to surface adsorption, chemical reaction, and possibly another step, and so on. So we can use a microfluidic reactor to go from 300-400 Celsius degree to room temperature, and the channel will go just like this. So really fast, from ultra fast thermal cycle, and figuring out at the end what we have. Mixing brine with different type of gas and see if we can have a chemical reaction. Minerals can also be integrated either in real minerals in the cold part to simulate the minerals that you can find at the seafloor, or hot part like pyrite or sulfide that you can find in the chimney. And to me, what is more interesting here is that you can mimic the cross section of a vent by injecting in on one side hot water and dissolved gas, meaning hydrothermal vent fluid from one side, and cold water, so typical of the ocean water on the other side, through a porous media that represents the porosity of the vent right here. And you have the thermal gradient, the pressure gradient due to the difference in velocity, the concentration gradient, and the velocity gradient. Under the microscope, you can do biochemical imaging, or in that case for prebiotic chemistry, chemical imaging, to monitor the presence of different type of molecules that could be created here. You can generate pores as well in this structure. So this is a model system, but pores, and try to figure out what is the maximum concentration that can be reached in a certain space. Like I told you before, confined space, maybe higher concentration, absorption of molecules on surfaces, and so on. And you can couple that with modeling, an example of modeling here, of a vent exiting the fluid, to compare basically experiment and modeling. The problem with microfluidics is that it's really tiny, so sometimes to be quantitative is quite complicated. Microliters volume, if you recover a sample, it's going to take ages to get enough sample to do mass spec, for instance, or GCMS. So it's interesting to have tools that are at a little bigger scale, and in particular transparent, or at least equipped with windows. Here, sapphire window or silicon window, to be able to combine FTIR environment to have multi-analysis on your sample in a single run. So that's what our colleague in Bordeaux at ISM, Thierry Tassin, has developed with Grégoire as well. And they wanted to recreate the hydrothermal pump. How do you do that? A smart way that was found is to put a cell here which is heated at high temperature, 400 Celsius degree, to represent the fluid coming out from the chimney. Another cell, high pressure cell, equipped in which you can put some minerals to do the catalysis, sulfide, and so on. And the upper phase, which represent, still under pressure, but which is cooled down and represent the ocean water system, I would say. Interestingly, when you heat this and you cool this down, heat this up, cool this down, you have a natural recirculation that occurs. Exactly what happened in the hydrothermal pump that I mentioned just before. You just have to maintain the temperature gradient from here to here to have a recirculation of the fluid from hot to cold, and then back to, if you close the loop here, the fluid is moving here and going back there. What is nice here is that you can see you have lots of sapphire or silicon windows here everywhere. So you can do Raman, infrared at different positions to evaluate the composition of dissolved gas in the liquid phase at low temperature, but also the gas headspace composition, CO2, nitrogen, methane, and also evaluate in real time the evolution of the mineral particles that are undergoing geochemical reaction due to the high temperature fluid that is going through. So if I get back to my point before with the thermal pump, this is what is seen, typically by Grégoire, through the sapphire window with pure CO2, system CO2 and water, different pressure and temperature condition, or when you use Fontainebleau sand in the high pressure cell for minerals. And just by maintaining low temperature at the bottom, high temperature at the top, you can see this flow that is observed right here at the exit of this tiny capillary that goes from high temperature to low temperature. So even by looking at the movies, you can determine velocity, speed, and so evaluate different kind of scenarios and predict potentially the speed of fluid that exiting an hydrothermal vent, depending on the difference of temperature between the hot area and the cold area. Numerically speaking, you can do exactly the same thing. It's quite interesting. You have this system, basic one. You heat up here, you cool it here. You can see the heating waves that are starting, and then the fluid that start turning naturally, just by maintaining the temperature difference between the bottom and the top. Numerical studies are also interesting to predict fluid flow in porous media. So this is a microreactor designed with a certain porous media design here, inlet, outlet, or inlet, outlet, well, it's reversible. Fluid will flow inside. So this could be hot fluid, cold fluid, for instance, and we can map the velocity of fluid in different sections depending on the permeability and the porosity of the rocks that could be used inside the microsystem, and compare this to the chemical mapping that I was mentioning before. Don't worry, it's my last part. I just want, and it's not going to be long because I think you had lots of organic chemistry this morning, much better than what I can explain. So my point was just to give you a few examples of chemistry that have been listed in the literature at hydrothermal condition toward matter complexification. So I'm going to go from small molecules to big molecules. So first thing is to start with the synthesis of hydrogen cyanide. So it's really easy to form in the condition that we are using, 200 Celsius degree, a different kind of pH depending on molar concentration, from ammonia and carbon monoxide, for instance. This is a typical reaction that can occur. It's 2, sorry, it's not 22. And there's a chemical process developed by Degussa also, which is well known, when you can use methane and ammonia to generate the hydrogen cyanide. 1000 Celsius degree and a PT catalyst. Keep that in mind because I'm going to get back to this point almost at the end of this presentation. Those conditions are not really realistic. Well, this process can occur also without PT, but probably the kinetics would be much lower. Formamide also can be formed after the absorption of this hydrogen cyanide molecule in water, and using formic acid and derivative to form to form formamide. Formaldehyde the same way can be formed right here from the interaction between water, CO2 and carbon monoxide through a reduction, except that methanol and CH4 are not really stable. Kinetics goes this way, are not really stable under hydrothermal condition. You generally get back to oxidation due to the oxidation property of water. So all these molecules can be made with such process. Then there are other different type of synthesis. I'm not organic chemist, so I'm not going to detail that much. But different processes were reported also in the literature for the synthesis of different type of other molecules such as amino acids and others. So you have the Strecker synthesis, the Bircher-Berg reaction that I'm not aware of, but trust me, it works. And they also can combine different amino acids to form peptides which are one of the key elements that we need, one of the 3 key elements that we need later on. So amino acid can be made also from a different reaction of pyruvate with ammonia to form alanine, or like that if you reduce with hydrogen. In that case, it was demonstrated that the increase of temperature has no real effect on the yield when you run short experiment, which could be representative of the condition we are investigating. And through decarboxylation process that can occur also at high temperature, that could work, but depending on the temperature system, I'm getting back to what are the temperatures that we need to consider for late ADN, early Archean vent. If you go too high temperature, this step is clearly limiting, so you get back to the reverse reaction. Sugar can be made also with a four-Mohs reaction, so starting from the combination of different smaller molecules with glycoaldehyde through isomerization to form pentose and hexose that are starting point to ribose. And monosaccharide can be also made with a catalysis such as calcium hydroxide, which we can find right now, like I told you, in white smokers. So again, adsorption of molecule on surfaces, catalysis through minerals helps definitely to form this type of thing. So all these reactions have been demonstrated in batch mode. So it could be interesting to get further and figure out whether kinetics can be speed up when you work in flow. You start making ribose molecules that are the starting point for DNA. I'm going to switch this, but nucleobase can be made as well through different chemical pathways, starting from hydrogen cyanide to form adenine, guanine, uracil, thymine. Where's thymine? Somewhere. I'm not going through that, but all these things can be made in water at supercritical or subcritical condition, which are representative from the vent. Lipids as well. Indeed, you can use the Fischer-Tropsch reaction to combine carbon monoxide with hydrogen and form different carbon chain lengths towards the formation potentially of membrane, assembly, auto-assembly later on, compartmentalization. So depending, here you have different yield depending on the temperatures that have been reported. But in brief on this, so I was quick on this organic chemical part, but first, I'm not an expert. Secondly, just to show you that this definitely works. So it's important to keep in mind that organic chemists can do whatever they want. No, but seriously, you say, can you make this? Sure. I'm going to use 5 kilograms of platinum, UV, blah. So is it really representative from early Earth conditions? So it's important to, if you want to work on this type of system, to consider this way. So you start from potential early Earth condition to run your probiotic experiment, but also to consider the chemist feedbacks to say, if I put this, I can make what you want. Can we find me condition on Earth at this time that could be representative? And this loop can definitely be useful, because if you, again, I mean, working with organic chemistry, say, sure, it's going to be easy. But yeah, but I'm working on prebiotic chemistry, so I'm not sure that I can be really representative from the condition I'm talking about. Yeah, don't worry. Of course, don't worry, but is it really true? I'm not sure. So conclusion, I like this picture because it's, would say, life emergence in one egg, but among different type of things. So it could be hydrothermal vent, I showed you, but it could be other solution as well, and it could be also a mix of different kind of things. So I hope that I was able to show you that these chemistries are clearly doable in such environment for the 3 different parts that are needed: lipid, phospholipids, for compartmentalization, RNA, potentially DNA work later on, and the enzyme synthesis. Small molecules can be easily abiotically synthesized. It's a little bit still more complicated to figure out. There are papers, definitely, but to figure out how to start easily polymerization process for these tiny molecules toward proteins, toward phospholipids, and so on. But like I showed you, example exists, especially due to the use of mineral surface, clays or microstructure, porous structure, confined environment, that are really interesting for concentrated, for increase the concentration of species and use the reactivity of the mineral surface. And this reactive surface help catalyzing the chemistry, of course, and also stabilizing reactive intermediates before they are degraded by external condition. But you've seen also that the investigations at lab scale are quite complicated because it requires multi-competencies. You need organic chemists, you need geochemists, you need thermodynamics, hydrodynamics, and experimental means that are not easy to fabricate, reactor, characterization, and so on. And that's what I mentioned before. The interest we see here is that it's important to try to speed up the rate at which reaction can be carried out, to generate database of possible scenarios and database of chemical reactivity, because once you have a sufficiently large database, then now you have redeveloped AI approaches that can be used for predicting chemistries that could occur and help you back in your work to try the hypothesis proposed by AI. But like I said, keep in mind that hydrothermal vent, yes, but those systems were not isolated, and they are still not isolated. And there are lots of mass transfer between hydrosphere, atmosphere, and lithosphere that are of primary importance. And maybe one reaction could have occurred in the atmosphere, molecule dissolve in the water, get back to the hydrothermal vent system where another kind of molecule could have been created and then combined. We talk about mass transfer in the time scale of maybe thousands or even more years, but this is the carbon cycle, and all this kind of cycle are predicted and are known on Earth right now. It's important to keep in mind that such systems were also present at this time and could have clearly impact the chemical reaction. Just to finish, we were recently with Hervé, by the way, also, and Vasilisa and Anaïs. We got a research project at the national scale called Origin, with a targeted project which is called microfluidics, with different labs, or one in ESPCI in Paris, Marseille University, and another lab in Bordeaux, starting this year with the development of a huge microfluidic platform to study whatever I told you before. And we have 3 years of postdocs available. So for those who are interested, please contact me or Anaïs for application. And thank you very much for your time and effort after your lunch.